In this video, we'll be talking about the most important theorem so far, Cauchy's theorem. This is important because it's going to let us lay a lot of the groundwork for future videos and proofs, so it's important that we understand it. So, unlike previous videos, we're going to jump right into the main point of this video. We're going to go right into Cauchy's theorem. So what I've written in green here is Cauchy's theorem. So let's just read it. It says, suppose f is analytic, so remember analytic means differentiable, on some domain D. Let gamma be a piecewise smooth, simple, closed curve. So that's a lot of modifiers. So if you don't remember what piecewise smooth, simple, or closed mean, go back to the sets video, refresh yourself before you come back to this video. So it's a piecewise smooth, simple, closed curve in D, whose inside, omega, is also in D. Then the line integral of f of z dz over this gamma is going to be equal to 0. So what does this all mean? Before we prove it, let's try to make sense of it. So first thing, it says we have a domain D. So I've drawn this purple domain D, and remember a domain is an open set. So this outside boundary, this purple line, is not included in the domain. So next thing is let gamma be a piecewise smooth, simple, closed curve in D. And since it's in D, it can't touch the boundary because the boundary is not part of D. So this orange loop right here satisfies all these conditions. It's a piecewise smooth, simple, closed curve that's fully inside D. We're going to call this gamma. And I've given it a positive orientation since the inside, which we're going to call, the inside is named omega. So the inside I'm going to put in brown, and this is going to be omega. That is always on the left as we travel in this counterclockwise direction. Okay, so whose inside is also inside D. So all the premises of this theorem are satisfied. Then the line integral, so really it's a loop integral, it's closed because we're going to go all the way around this loop, is equal to 0. So what does that mean? So let's pick a starting point. Let's say we start right here, this big orange dot on gamma. Now, at that dot, we take the value of f of z, whatever that function is. So we take that, and then we move to the next point on gamma, and then we take the value of f of z there, and we do that. We keep doing that over and over and over again until we get back to our same point. And then when we add up all of those f of z's, that's what the integration is, we're going to get 0 according to this theorem. So this seems a little bit weird. It might be even counterintuitive because you're thinking when you add a bunch of stuff up, how can they be 0? So the way they can be 0 is if some of them are negative. So let's go ahead and prove this. The lucky thing for us is that this proof is not that difficult, and it's pretty elegant and uses a lot of things that we've learned before, so it'll help us kind of refresh ourselves. So we'll start by writing out what we're seeking to find. We want to find the line integral of f of z dz over gamma. And now, if we remember from Green's theorem video, we can convert this into a double integral because it satisfies all the conditions necessary. So if you go back to that video, you'll see that we can do this by doing double integral over the inside. So that's going to be omega. And inside here, we have to put partial f partial x plus I partial f partial y. And then we put dx dy. Okay, so it got a little bit cramped. So this says I times double integral partial f over partial x plus I partial f over partial y times dx dy. And this is all over the area omega. So now this seems a little bit even messier than this. So what are we going to do with this? So now we're going to take the inside, the integrand, and we're going to see what we can do with that. So df dx is equal to what? So f is u plus iv, correct? So we'll say f equals u plus iv. And so we can split this up as du dx plus I dv dx. And the same way we can split up df dy as du dy plus I dv dy. Now why does this help us? This helps us because now what we're going to do, we're going to add these two together. We're going to put I in front of this. So this is going to get I in front of it, and this is going to get I squared, which is going to make it -1. So, and then we're going to add these two things together just as they're done, just as we do right here. And we're going to get du dx, and then we're going to get plus I dv dx, and then we're going to get plus I du dy, and then we're going to get minus dv dy. Now let's notice something else. So we're going to use a result from a previous video, the Cauchy-Riemann equations. So what did one of the theorems we talked about said? One of the things that are the premise here says f is analytic on the domain D. And remember, one of the theorems we talked about said that if it's analytic, Cauchy-Riemann equations are met. So how does that help us here? Cauchy-Riemann equations say that du dx equals dv dy. So if we subtract them, as it's done here, we get 0. So these actually cancel each other out. What else do Cauchy-Riemann equations say? Cauchy-Riemann equations say that dv dx is equal to negative du dy. So if we write this here as, we factor the I out, and we have dv dx plus du dy, this inside portion here equals 0 by the Cauchy-Riemann equation. So really what we have here is 0 plus I times 0, which is just 0. So what equals 0? If we trace this all the way back to the beginning, this equals 0 by an application of Green's theorem and by an application of Cauchy-Riemann equations. So this equals 0. So this proof is done. And it turns out this is very important. This is the most important proof, that this is the most important theorem that we've done so far, because it lets us talk about closed loops, and not just closed loops, things that make closed loops. So for example, if this was one curve from this orange dot to this brown dot, and from the brown dot to the orange dot was another curve, we can talk about those two curves being equal and things like that. So we'll see that right now. So the next thing we're going to talk about is a new definition. So simply connected. This definition deals with domains. So we're going to say a domain, and we'll just call it D, as we've been doing. A domain D is simply connected. I'll put simpcon. It's simply connected if what? It's simply connected if when gamma is a simple closed curve in D, the inside of gamma, which we've traditionally been calling omega, so we'll call it omega again, the inside of gamma, omega, is inside D as well. So let's just draw two quick examples of something that meets the simply connected and something that is not simply connected. So first let's draw something that is simply connected. So this is easier. So here's a graph, and let's go ahead and draw a domain that is simply connected. We'll just take this one right here. So this purple domain, so again it's just the inside. This is simply connected because whenever we draw a closed simple curve in here, so we can draw any closed simple curve. So I've drawn one orange, here's another one over here in orange, here's another one. Anytime we draw any closed simple curve, the inside of these curves, so if we paint them, if we color them in, all of that is inside the purple. And there's no way to draw a closed simple curve in here so that the inside is not inside the purple. Now, let's do an example where this is not met. So this is not met in this example here. Let's say our domain is an annulus. And an annulus is a fancy name for a donut or a ring. So it's just this. It's still an open set, but now it's just the inside of this ring or donut. So this inside hole right here is not part of the domain. So now, is it possible to make a curve gamma so that gamma is inside D, but the inside of gamma is not inside D? Well, first let's look at this curve right here. This orange curve right here. This does satisfy the criterion because this curve right here is inside D, and if we paint it, then everything in here is also inside D. But we can easily break this criterion by making any curve that circles the middle. So this new curve in orange, in fact, let me do a new color to illustrate this. So I'm going to put this new curve in blue. So this new curve here, this curve is fully inside D because it's fully inside the purple area. But if we paint this, if we color the inside, we're going to start getting points that are not inside D because this includes the entire center hole, and none of the center hole is in D. So this domain here, this annulus domain, is not simply connected, but this is simply connected. Okay, so this will be important in the next theorem, which we'll prove just by a little picture. No complicated proof for this one. So Theorem B says that let D be a simply connected domain, so what we just talked about, and let gamma be a closed curve in D. If f is analytic in D, then again we have line integral f of z dz over gamma equals 0. So you're probably asking yourself, how is this theorem right here different from the Cauchy's equation, Cauchy's theorem? So how this is different is, notice here we had f analytic on a domain D. Also here we have f analytic in D. But the thing we have here is that what are the restrictions on gamma? Gamma had to be piecewise smooth, simple, closed. What's the restrictions on gamma here? We say that gamma is just closed, no other restrictions. And the biggest restriction we've taken away is simple. So back there on the previous side of the paper, where we had to have simple, where the curve did not intersect itself, here, this is basically Cauchy's theorem with the condition that and we allow the curve to intersect itself. That's okay. So we have to kind of prove that it's going to work for this as well. So we're going to illustrate this just by a simple example, no complicated proof for this theorem. So how we're going to do that, I'm going to use a little bit of color coding so we can, it'll help us out later. So I'm going to draw this portion in blue, I'll draw this portion in red, and I'll draw the last portion in green. So this is all one curve, even though I've drawn it different colors. So I'll use black to illustrate the direction of motion. So let's say we start from here. This is the starting point. Then we travel this way along the blue curve. We make a loop like this around the red curve, and we come back to our home base, this point, on our green curve. So ensure that this is closed. This is closed because the starting point and end point are the same. It is not simple because there's a self-intersection right here. So is Cauchy's theorem still met? Is the integral over this whole curve, which we're going to collectively just call gamma, is the integral over that curve of f of z dz just some function that's analytic in the domain? So other thing we can note is that this is inside some domain. So all this orange is going to be the domain that it's inside, just as a technicality. So it's inside that domain. Is the integral still 0? Well, let's look at something. We're going to break this gamma into 3 pieces, which is why I color-coded them. So the blue piece we'll call gamma 1, the red piece we'll call gamma 2, and the green piece we'll call gamma 3. Okay, so collectively, it's pretty obvious to see that gamma as a collective unit equals gamma 1 plus gamma 2 plus gamma 3. So how can we represent integral of f of z dz over gamma? Well, if you go back to the line integrals video, we can split up this into 3 integrals. We can split them to gamma 1, f of z dz plus integral gamma 2, f of z dz plus integral of gamma 3, f of z dz. Now, one of these integrals we know is 0 right off the bat. Look at gamma 2. So pay attention to only this red curve. What is this? This is a closed, simple curve. This is simple because this red curve itself does not intersect itself. And it's closed because it starts at this node right here and just goes around and ends up at that node again. So that means the integral around this curve is 0. So gamma 2 curve, we can go ahead and just cross that out. That's 0. Now what about the remaining 2 portions? We have integral over gamma 1, integral over gamma 3. Let's combine them to make integral gamma 1 plus gamma 3 f of z dz. So what do we have if we have gamma 1 plus gamma 3? Well, we have this blue part, and then we kind of just skip over the red part, and we just go ahead and take the green part. So we have the counterpart of this red part. We have the rest of the curve. So this, again, is also close, because we start at this node right here, go over here, we end up at this node, and then from there we just continue on back to the beginning. This is closed and simple as well. So the same argument applies. It is also, the integral over it is also 0. So we say this is 0. And since all of this just zeroes out, we say that the initial thing we wrote down, the integral of f of z dz over this gamma, the entire gamma, is 0. So the very cool thing about this is that we had a not simple curve, something that intersected itself, and we broke it up into simple curves. And the truth is you can always do this. You can always break up into simple curves, and the integral over each simple curve is 0. So the integral over the whole thing, whether it's simple or not, is going to be 0. So this is going to be useful for us later on as well. So the last thing that we're doing in this video is talking about Theorem C. So let's first just state the theorem and talk about what it means, and then we'll prove it. So Theorem C says that if f is analytic in a simply connected domain D, then there's an analytic function, so a differentiable function, f, big F, on D, with big F prime equals f throughout D. So what does that mean? That means that if f is analytic in a simply connected domain D, so let's go ahead and draw a simply connected domain D. Here's a simply connected domain D. So we're going to say our small f is analytic throughout all of this. Then there is an analytic function, big F, on D. So there's another function. There's some unknown function, but it exists. Some big F on D, on the same domain, so that when you take the derivative of this big F, it always gives you small f. So that basically, what this is saying, Theorem C is saying that if f is analytic in a simply connected domain D, then it always has an antiderivative in D. So take note that big F is an antiderivative of f, because big F prime equals small f throughout all of D. So that's the important thing to note. The rest of this video is just going to be a proof of this, and I will admit that it's pretty long, so if you're satisfied with this and don't want a proof, you can stop here. If you want to, then that's great. Let's move on and try to prove this, because it's pretty rewarding as well. So let's start the proof right here. So it's not that difficult of a proof to go through, it's just kind of long. So we're going to fix a z0 in our D. So this D I've drawn in, now it's green. So we're going to fix some point in z0, so right here. And we're going to define big F of z as integral of f of w dw over some curve gamma, where gamma is any curve from z0 to z. So this is a little bit confusing. Let's just let's shed some light on it. So we're going to now take this integral and frame it in terms of a function. So now let's say you put some z in here. Let's say you put this z, this point right here. So now what this function is going to spit out to you is the integral of f of w dw. We're using w here because we put z here. So it's the same thing. It doesn't matter if you put z or w here. So f of w dw over this curve gamma that connects z0 to z. Okay, so we're just taking the integral and we're framing in terms of a function. So the input of the function is a point, the output is the integral over a curve to that point. The next thing we want to show is that it doesn't matter which path you choose from here to here, it should always be the same. So how we're going to do that is we're going to say gamma sub 1 is another such curve, which is another curve that connects z0 to your point z. So here's gamma 1, here's the gamma. Then big gamma, which is represented, or uppercase gamma is represented by this kind of right-angled L that we twisted around, is equal to gamma minus gamma 1. So let's remember what minus curve means. When you take minus a curve, you reverse its direction. So gamma minus gamma 1 is first traveling on gamma, and then traveling on the opposite of gamma 1. So we're going this way. What do you notice about gamma minus gamma 1? It's a closed curve, which means that Cauchy's theorem does apply to it. So it's a closed curve in D so that the integral over it is equal to 0. But what is it also equal to? It's also equal to the difference of these two integrals, because big gamma is just gamma minus little gamma. Or sorry, it's equal to gamma minus gamma 1, and the integrals over each. So what else does this tell us? Let's just look at this section right here. Since this integral minus this integral is equal to 0, that means this integral is equal to that integral. So that means that whether you take the integral of f of w dw over gamma, whether you take it over gamma 1, it's the same thing. And this would apply for any curve. So I could choose literally any curve as long as it's in D, the domain that connects z0 to z, and the value of the integral, so the value of f of z, will be the same. And it was important for us to show that because we need to establish that f of z is a function, which means that it has the same value no matter what z you put in. So when you put one value of z in, it only has one value, and that's what defines a function. Okay, so the next thing we'll do is tackle the main point of what we're trying to prove, the antiderivative part. So this proof has a lot of pictures, so let's start the antiderivative part. So wipe your plate clean. So all the definitions of z0 and z, wipe them clean. We're going to start over on our definitions. So next thing we're going to do is say, let z sub 1 be an element of D. So the domain is the same here, and here's z sub 1. And let R be a number small enough so that this whole thing right here in brackets just represents a disk. So remember, it's z minus z1 modulus is less than R, which means that the disk centered at z1 with radius R is inside D. So what I've drawn here is, here's z1 again, as I noted, and here's R. This little purple disk right here has radius R, and it's an open disk. So this disk is small enough so the whole thing, open disk, lies completely inside D, which is what this line stated. Now we're gonna define some new complex number h, and that complex number h is gonna have modulus less than R, and let L be the curve joining z1, z sub 1 to z sub 1 plus h, composed of a horizontal and vertical segment. So if you're lost here, let's go over what exactly is going on. So we defined a point z1, and then we put a circle around it so that the whole circle is inside D, this green domain. Now we defined a new complex number h, so that z1 plus h lies inside this purple disk. And why does it lie inside this purple disk? Well, that's because the modulus of h is less than R, which kind of is another way of saying if you take the distance of h, how long h is as a complex number, it's going to be less than R. So if you add that h to z1, it's not going to exceed the boundary of this disk, because the boundary of that disk is radius R. Okay, so the next thing we did is we have z1 and we have z1 plus h, and it's true we can connect them in many different ways, but we specifically want the path that consists of one vertical and one horizontal segment. So here I've made a bigger picture. Here's z1 plus h, and L is the path that connects them with a vertical and horizontal segment. So here's the right angle to show that these are perpendicular to each other. And this distance from z1 to z1 plus h is modulus h, because that's how distances between complex numbers are formulated. Okay, so two things to note before we go on in the proof. Note that since neither leg of L is longer than its hypotenuse, and this is just something from geometry, neither leg of a right triangle can be longer than the hypotenuse. So that means the total length of L, which is this plus this, has to be less than 2 times the hypotenuse. And just take a minute to reassure yourself that makes sense, because if you have this leg is less than the hypotenuse and this leg is less than the hypotenuse, then added together, they have to be less than twice the hypotenuse. So we have length L is less than twice hypotenuse. That'll be important in just a second. Also, note this integral. The integral of just dz over L is equal to H. And it's weird sometimes seeing nothing in there. So really, I guess you could put a 1 in there. But this integral is normally defined as a length integral because all you're doing is just moving across L, this right angle piece right here, and you're just adding 1, 1, 1, 1, 1. So really all you're doing is just taking, you're going from Z1 to Z1 plus H. So all you're really doing is you're capturing the vertical and horizontal component of H. So in all you're capturing is H because you're just capturing the difference between Z1 and Z1 plus H, which is H. Okay, so keep that in mind too. So the next thing we're going to do is we're going to let gamma sub 2 be a curve joining Z0. So remember, that's been floating up here, doing nothing so far. Be a curve joining Z0 to Z1 plus H. So I've drawn that in pink here. Z0 to Z1 plus H, okay? And gamma is a curve joining Z0 to Z1. So this is going from Z0 to Z1. So now we have this kind of loopy looking thing because we have something from Z0 to Z1, we have something from Z1 to Z1 plus H, and we have something from Z0 to Z1 plus H. Only problem is they're not all going the same direction we want. So we're going to define this new curve, big gamma. So this is different from the one on the previous side of the paper because we define new things here. Big gamma is equal to, so let's trace it. It's equal to gamma 2, so we're going to start by tracing out gamma 2, minus L, so we're going backwards on this right angle bracket, minus gamma, so we're going backwards on this. So we have a complete closed curve here. In red is a closed curve. So therefore, since it's a closed curve, Cauchy's theorem applies, and the integral of f of w dw over this big gamma is equal to 0, as before. And now, again, we can break this up into its components. So we have it's equal to the integral over gamma 2 minus the integral over L minus the integral over gamma. And then here's the next thing to keep in mind. So the back of the paper said that this function, big F of z is defined as this integral, where gamma is the curve from z0 to whatever z you put in. And notice that two of our curves satisfy that criterion, because gamma was the curve from z0 to z1, and gamma 2 was the curve from z0 to z1 plus h. So they can both be framed in terms of the big F function. So gamma 2 was the curve from z0 to z1 plus h, so it's f of z1 plus h. This we just leave as is. And this gamma was the curve from z0 to z1, so it's going to be f of z1. And again, that all equals 0. Okay? Now let's move on. Next piece of paper. So we have we have this right here. So what we're going to do is move we're moving the integral of f of w dw over L. We're moving it to the other side so it can be positive. So that's how we got this first line here. Now we're going to divide everything by h. So we're dividing this by h, we're dividing this by h. So we put 1 over h. H is a constant, remember? It's just that it's that difference between z1 and z1 plus h. Now we're going to do something weird, which will make sense in a second. We're going to subtract from this, we're going to subtract h times f of z1 over h. So we're putting two h's, but it's important on this side. So here we have 1 over h times this minus h times f of z1 over h. Okay, so now what do? Now this side we can take the h's away. We can just put f of z1 equals 1 over h times this integral. And now you're probably asking, where did this integral sign come from? Well, this f of z1 is a constant, right? Because z1 is a constant and f is just a function, so it spits out some constant number. So we put f of z1, and we took this 1 over h and this 1 over h here, and we factored it outside, but that still leaves us with an h here. So how did this h transform into an integral? Well, that's why I said back here, note that integral of dz over L is equal to h, because that's exactly what we have here. We have integral of dw, just a different variable, over L is equal to h, so we frame it in terms of an integral. And why did we do that? We did that because now we have an L integral here and we have an L integral here, so we can easily combine them. So now we have here equals 1 over h times integral f of w minus f of z1 times dw. And we did that by just subtracting this from this because they're both common L integrals. Okay, so next thing we do is we left this how it is. We took this 1 over h, we brought it to the inside because it's just a constant. And now we're going to do something that you need to go back to a previous video if you don't remember. So in a previous video, we derived, I believe it's probably the Green's theorem video, where we define this estimate, this integral estimate, which I said was very important. So because we're going to use it now, we're going to use it later on. So this integral estimate says that integral of some function u of z dz over some curve gamma is less than or equal to the maximum of modulus u of z on gamma times the length of gamma. Okay, so we're going to apply that to our example. We're going to apply it to this integral right here. So since we're going to apply to this integral right here, so what we're going to do is take the modulus of both sides. So we're going to take the modulus of this side right here, and that must be less than or equal to the maximum of, we're going to say modulus f of w minus f of z1, which is exactly what's right here. And you're asking where did the modulus h go? Well, I put that on the end right here because we can just take it out, times the length of L. And we don't know exactly the length of L, but the other note I said to put, the other note was that length of L is less than 2 times length of h. So I put that here, times 2 times length of h. So to recap, this is in modulus because this is the same as this in modulus. So this integral in modulus is the same as this whole f, big F, small f in modulus. So that collectively is less than or equal to the maximum value of modulus f of w minus f of z1 on L. So this is a w when w has to be on L, times 2 times modulus of h. And I put that because that is an upper bound for the length of L. And 1 over modulus h just comes from here. I just factor that out. So as you've seen, I crossed out the modulus h, which is good. That's gone. So we're left with just less than or equal to 2 times maximum of this difference, this difference in the modulus, where the w has to be in L. So we are almost done with this. Okay, so now we want to take the limit as h approaches 0. And we want to find the limit as h approaches 0 of this, because this is starting to kind of look like a derivative thing, and we would like to see if we can follow through with that. So we're going to take the limit as h approaches 0 of 2 times maximum of modulus f of w minus f of z1 when w is on L. So let's go back to a picture and see if we can figure that out. So this is a mod we want to see as limit as h approaches 0. So as h approaches 0, so let's say it's getting really close to 0, this whole L thing right here is getting really, really, really small. So what's happening to this f of w minus f of z1? Well, we have f of z1 is fixed, so this is fixed. But f of w, which is any f of anything on this L-shaped thing right here, is getting really close to z1. So the difference between anything on this L and the difference between that and z1 and f evaluated at that point is getting really close to 0. Which is why limit as h approaches 0 of 2 times maximum equals 0. Now we are pretty much done because everything we have derived so far will lead us to this conclusion. Since we said that this in this magnitude here is always less than or equal to this value right here, and the limit of this equals 0 as h approaches 0, then we can say this limit equals 0. Because since if something is always less than something else, and this limit is 0, then this limit must be also 0. Because this has to be a 0 or positive number since it's in modulus, so the limit has to be 0 or positive. And if the limit is less than or equal to 0, the limit has to be 0. And we can take off the modulus, because if the limit of the modulus equals 0, the limit without the modulus also has to equal 0. Because that's the only way that can happen. And now we just kind of reframe it here, and we get limit of this big F of z1 plus h minus big F of z1 over h as h approaches 0 equals f of z1, so small f of z1. And this is defined as the derivative. So after all that work, we are finally done. We found that this derivative exists, which is why I put that here, and furthermore, it's equal to f of z1. So we have big F prime of z1 is equal to f of z1, just as we wanted all the way over here at the beginning. Okay, so the last thing I would like to do is a really quick corollary. You don't have to watch this, it's just something I crammed in at the bottom here. So the corollary says that let f be analytic on a simply connected domain D, and let gamma be a piecewise smooth closed curve in D. Then the integral of f of z dz over gamma equals 0. How do we prove this? Suppose f is a function on D with f prime equals f. Why are we allowed to suppose that? Because f is analytic on a simply connected domain D. So Theorem C says that if f is analytic on a simply connected domain D, then there is a function such that big F prime equals small f. So we can say big F prime equals small f. Then we can say this integral, which we're interested in, equals this integral. I just substituted small f for big F prime. So then, since going back to single variable calculus, the details aren't included here, but we see that generally we have an integral and then we have a derivative. So when we have an integral and a derivative, it's using fundamental theorem of calculus. It's going to be big F, so that function of the endpoint minus the function of the initial point. And what's the last piece of information we need, that it's closed, which means the endpoint is the initial point. So f of endpoint minus f of initial point is just going to be 0, which is why this is 0. So that was a lot of explanation, but trust me, it was all necessary, and it's going to help us a lot in the future videos. So until next time.